Welcome to the beginning of our very exciting seminar series. I think we have never seen this room so full. So we want to duplicate this as we go forward. This is a very special event because not one, but two industry partners of this institute they are sponsoring this seminar today. One of them is our close partner, IAI. They are located in Rockville, and they have been sponsoring our seminar series for the last 6 to 7 years. If you hear me, thank you, IAI. Really grateful to you guys. We are streaming the seminar live for the IAI. And the second industry is Northrop Grumman. They're located in Baltimore. And Microsystems seminar series. So this is a joint sponsorship, and I'm thrilled to introduce our speaker, Professor Alireza Khaligh. Alireza has been with
everywhere. We have people that are looking for DOE or another member. So this does not include our undergraduate members. Only I have included 2 of most recent undergraduate members. So we had like more than like close to 40 undergraduate students that they were research assistants in our group. So our research is focused on power electronics and application of power electronics for a variety of applications. So if you don't know what is power electronic is an enabling technology to produce, convert, transmit, and use the energy wherever you need. Okay? So we do power electronics for a variety of applications, for transportation electrification, which includes plug-in hybrid electric cars. Our research has mainly focused on 2 subjects in plug-in hybrid electric cars: chargers and hybrid energy storage systems. Then we have also worked on and working on more electric aircraft. So we're doing power supply design for more electric aircraft and looking into next generation of shipboard power systems. So DC-DC converter, AC-DC converters, EMI problems, how you can alleviate the concerns. Also, we have looked into power electronic interfaces for micro-robotics, energy harvesting, and we have recently started to look into power electronics for data centers. So I'm going to start my presentation for power electronics for transportation electrification, mostly electric vehicles, and then I'm going to explain to you what are the charging challenges and hybrid energy storage challenges, and then I'm going to move on to the next topic. I don't want to focus only on single topic because it's going to take a long time just to focus on single topic. So if you look at a plug-in hybrid electric vehicle, you would see there are many components in a car which requires power electronics. You have, first of all, in electric cars, the motion is electric, right? So you need to have a propulsion machine, which would act as a motor or as a generator. You have a DC-AC inverter, that's a propulsion inverter. Sometimes between that propulsion inverter and the large battery pack, every electric car or plug-in electric car is equipped with about 400-volt large battery pack. And so you need to have a DC-DC converter between that large battery pack and the inverter. And then before that, you need to be able to charge the battery, so you have an charger, onboard charger, which is that AC-DC and also isolated converter. Look and see if I can have a pointer. But anyways, and then in addition to that, we have another small battery. Every car has now 12-volt battery, right? So there's always a, thank you. There's always a DC-DC converter between this large battery pack and small 12-volt battery pack to provide power to your auxiliary, to your wiper, to your air conditioner, to your music player, and all those things. So all of these are power electronics, right? So if you look at the weight of an electric car, 30% of the weight goes to battery, another 30% goes to power electronics and motor drive and all those things. So these are also very expensive. It's been huge investment from Department of Energy, a lot of governmental agencies on battery, improving the battery. Power electronics also, there has been a lot of investment, but not as much as the energy storage. So if you can reduce the weight of these power electronics, or even if you can improve their efficiency by 1 to 5%, that's significant improvement. So these are all opportunities for us. I remember 5 years ago, I got an email from one person in Chrysler that they had, I think, like 100 or 150 openings for engineers with background in electrical engineering. Because traditionally, they used to hire always mechanical engineering students. Now everything is changing because everything is becoming electrified. We need a lot of electrical engineers that they are graduating. We need you, right? Industry needs you. So let's focus on only onboard chargers. Onboard chargers, I have a very small table here. If I want to include every car, this table could be like 5 pages. But I have like a small table showing a few of the samples cars that I have included here. Their price, their battery size, battery capacity, and the way that they have their onboard charger. I mean, most of these cars, they are equipped with onboard and offboard charger, right? If you know, every electric car can be charged with an onboard charger, and on top of it, electric cars, they can be charged with offboard chargers, which are really large chargers, and you can quickly charge the battery, let's say, in less than 20 minutes, less than half an hour. So I'm mainly focused on onboard chargers, but yeah, offboard chargers is a different subject. I'm going to a little bit mention about how we can even improve the technology of the offboard chargers as well. But main topic is not offboard chargers. But the ideas which I'm going to mention here, they are applicable to offboard chargers as well. So this is, like, as you see, this is a simple Tesla. I took this 2013, so a long time ago now. Everybody knows what is Tesla. In 2011, when I used to talk to people, I'll say about Tesla, at least I would tell you 80% of the people didn't know what is Tesla. So this is good, like a lot of publicity on electric vehicles. So majority of these cars, and I can say all of them, they have a connector which is compatible with SAE J1772, which is the US standard. So if you use, for example, charge a Nissan Leaf with 24 kilowatt of battery using a level 1 charger, level 1 charger is any charger which is on board and its output power is less than 1.9 kilowatt. Level 2 is anything less than 19.2 kilowatt, right? So if you use a level 1 charger, it will take 22 hours to charge a battery, which is whatever you have like plugged here, right? But if you do level 2 charger, it will take 8 hours. But if you go level 3, which is off-board fast charging, it would be less than half an hour, right? So we want to look at the structure of all these chargers. Whatever your charger is, independent of level 1, level 2, level 3, they have this structure. there's an EMI filter. This is the grid. AC-DC stage. In the case of level 3 or fast charger, this is a 3-phase system. In the case of onboard charger, it's a single-phase system. That's the only difference. And then you have an isolated DC-DC converter to make sure that you, to provide galvanic isolation and safety. And then you have your output filter and you charge your battery. Now, what do we expect from each of these stages? From each of them, we expect to have higher efficiency, really high efficiency here. We also expect that it could rectify the input voltage, unit power factor correction. We want it to be as small as possible, and as I mentioned, as efficient as possible as well. Almost same things from the second stage, except the fact that we need to also provide galvanic isolation for safety. And also we expect to be able to step up and down the voltage, the input voltage of this stage, because the battery's voltage varies a lot. If you have a 400-volt battery, the battery voltage could go from 250 volt up to 420 volt, depending on its state of the charge. If it's fully charged, it could be 420. If it's like fully depleted, it could be 200, even 50 volt. We don't let it normally deplete less than 200 volt, but in my opinion, we need to design chargers that are able to charge batteries as low as 200 volt. And we need to definitely have a higher efficiency across the entire battery voltages from, let's say, 200 volt up to 420 volt. So what is the charging way or scenario? Normally, the way that we charge these lithium iron phosphate batteries, we have constant current and constant voltage area. So what happens is, initially, you're charging the battery with a constant current when the battery is fully depleted, and its voltage is increasing. The voltage of the battery is increasing, right? You're charging it with constant current. As soon as you hit, let's say, 80% or sometimes 85% of the state of the charge, then if you look at this shows for a single cell. Then we now regulate the voltage, because voltage is like fully at 400 or 420 volts. You regulate the voltage from now on, and then you reduce the current, because you cannot dump large amount of current inside the battery, otherwise you will sacrifice the life of the battery, right? So you do constant current, then constant voltage. Now, if you look at this chart, you will see here the voltage is small, current is high. Here voltage is high, current is low. So in majority of the charging process does not happen in full load, in full power. For example, if I have a 3.3 kilowatt charger, if 3.3 kilowatt only happens here at this point or vicinity of this point, the rest happens in light load or medium load, less power, 1 kilowatt, 2 kilowatt. Now, if you look at the chargers that are available in the market, they give you a charger of, let's say, 92% or 93% efficiency, but that 92 or 3% only happens at full load, which is only for a small period of the time. Nobody tells you or they try to hide their efficiencies here or here in the bottom, because their efficiency are in the 80%, so that's really low. We need to improve those. And this is not only for chargers, any power electronic converters. So this is a work we published in 2000, if I remember right, 13. So we came up with the idea, okay, how we can improve the efficiency of these onboard chargers. We thought of the way that people design. I don't want to go so much into the technical and stuff. That's what I have here, mostly results of our research. The way that they do, you have AC-DC stage here, then you regulate this at about 390 volt. The output of this. To be compatible with the universal input grid voltages, you regulate that for 390 volt. Then, because you're regulating this at 394, then this isolated DC-DC converter, which is sometimes used, it's controlled using pulse frequency modulation, not pulse width modulation, pulse frequency modulation. The frequency varies a lot. So if your frequency varies a lot, your efficiency, sometimes you are operating in areas that you can ensure zero voltage switching or zero current switching with, which is called, I want to use a word which is like not very technical. You eliminate the switching losses doing that, because anytime that you have switching, you have losses. But then when the frequency changes, sometimes you can't operate it there, so you have a high loss. But if we can regulate this voltage, depending on what is the battery voltage and depending on what is input voltage, which is not complicated method, then this is going to be a variable voltage based on these two inputs, and you can always ensure that this converter is always operating in its maximum efficiency point. So we call it maximum efficiency point tracking. That was one of the very first efforts that we did towards these chargers, and we built a 1 kilowatt prototype, very simple prototype, and we tested and we published. The results, I have the results here. So if you compare the efficiency of our proposed LLC converter using our proposed control technique as opposed to conventional LLC, you would see all the losses. So these are the core losses, the brown, conduction losses are green, and switching losses are in purple or blue. So you would see that this is the traditional, this is the way that we can improve. So we can improve the second stage efficiency at full load by 2% and at light load by 9%, which these are converted to about 6.7% improvement in the efficiency of the charger. So that's significant improvement in the efficiency of the charger, especially in the light load. Then we thought, okay, what are the next things? What are the things that we should do, or other researchers should do in power electronics? First of all, chargers should be bidirectional. Bidirectional means not only you should be able to charge a battery, but also you should be able to provide power back to the grid in case there is an emergency, in case there is no power at your home and you want to use your electric car battery to power your load, or in case you provide additional power to the grid. So future chargers should be bidirectional, even though a lot of car manufacturers, they don't like this. But we want to give that functionality. We want to make sure that that functionality is there. I mean, we'll see one day it will be used. I mean, maybe one day battery technology will be so much better that it wouldn't reduce the life of the battery. I mean, or the lifetime cycle of the battery could be, I don't know, 1 million times, like a supercapacitor. So then that we can use those. So we want to provide that as bidirectional chargers. One thing which is very important in designing these chargers, whatever you add on board of the car, you're increasing the weight of the car, right? That is not what industry is interested in. That is not what anybody's interested, right? You don't want to have additional load. You don't want to make your car heavier and heavier, right? Because it would require more power, more energy to move. So one of the ways that you can reduce the weight of these converters is to use integrated magnetic components. I'm going to show you something. Let me go back here. If you look at this LLC converter, we have a transformer here, and there's an inductor. People in power electronics field, they know sometimes in order to be able to regulate do the pulse frequency modulation with a good range for LLC converters, you need to have a larger resonant inductor. So that larger resonant inductor is this component here. Now, if we can integrate this one into this and only have one magnetic component, then you are eliminating one magnetic component, and these are heavy. They're heavy, they're inexpensive, and also bulky. You see, if there are like 4 bulky components here, 2 of them are what? Capacitors, and 2 of them are these inductors, right? I mean, this heatsink is not optimally designed for this. This is just a proof of concept. Heatsinks are also heavy. So passive components in general, what I'm trying to say, the passive components in circuits are the heaviest components. If you can eliminate or reduce the number of passive components, you can make them lighter. So that's why I mentioned another idea is to do integrated magnetic components. But it has its own complexity. In the research in the lab we can do that. When it comes for manufacturing, that becomes very challenging. So also capability of charging deeply depleted battery packs. As I mentioned, in the case of a single cell, we use a lithium ion from 2.5 to 4.2. If the voltage drops to 1 volt, where we call it trickle charge or pre-charge, normally we call the batteries deeply depleted, right? So chargers normally, they don't go as low as like 100 volt. It was interesting. I made this presentation to Ford like almost a year ago, and I mentioned we could design chargers that they can charge the battery from even 100 volt up to 420 volt. And one of the executives mentioned to me, then, I mean, that's not important, because if you leave your car at your home and then go for a trip and something happens and your battery is dead when it's reduced, let's say, to 100 volt, you take car to the dealer and dealer makes money and charges. I'm like, yes, but if I can provide it, if we can provide this without an additional cost, why not, right? So in my opinion, we need to look into it. But when the voltage drops to 100 volts, then the efficiency is even lower, right? But for you as a consumer, in my opinion, you don't care the efficiency. You want to just charge your battery and be able to move your car. You don't want to call to a tow company to come and take your car, right? So it's easy. You charge it with lower efficiency, with little bit slower, till you get to the point that the efficiency improves. But if we can design chargers which they even provide higher efficiency, even at as low as this voltage, it's even better. Another idea which I have had was the reduced stage onboard chargers. As I showed, there was EMI, AC/DC, DC/DC, right? 3 stages you need to design for a charger. Can we get rid of one of those stages and then have a charger which has only 2 stages? That's also possible. I'm going to talk about how we can do that later on as we move forward. And then integrated onboard chargers. This is the main research area in my research group, integrated onboard chargers. So we have focused on 2 kinds of integrated onboard chargers: integrated low power onboard chargers, integrated high power onboard chargers. So low powers are those level 1, level 2, how we can, let's say, as I mentioned at the beginning, you saw there are so many converters on board of the car, right? Can we integrate 2 of them, build 1 converter which does the functionality for 2? We're reducing the weight by 50%, right? That's what I call by low power. And in terms of high power converters, like a car, let's say a Tesla Model S, has an 185 kilowatt hour propulsion machine and its inverter. So it's really large power. Can we use that propulsion machine's winding as our passive inductive elements, right? Passive power factor correction element to provide power factor correction and use the reverse path to charge the battery as opposed to having an off-board charger. Then we eliminate the need for off-board chargers. So that's what I'm going to talk a little bit more as I move forward. I'm sorry, I know I have a lot of subjects to cover. If I want to talk, it will take like 2-3 hours, but I'm just trying to go fast. So these are the topics that I'm going to talk. To achieve some of those objectives, we started with a new topology, which we call it bidirectional parallel resonant stage onboard chargers. So instead of having a single LLC converter, which doesn't have high efficiency in low and medium power, we can design an LLC converter which gives us or we can design a 2-stage, which is a low power LLC. Instead of, let's say, instead of a 3.3 kilowatt LLC, we design a 1.1 kilowatt LLC and 2.2 kilowatt SRC. What are the differences between these 2? SRC, your elements are in series. So what happens in the case of SRC, efficiency of SRC is really high. You don't have much losses in your magnetizing inductance. However, the problem with SRC is that you cannot, if you look at the transfer function of SRC converter, you cannot regulate the output voltage because the transfer function is always less than 1. VO over Vin as a function of the frequency. If you look, it's always less than 1, so you cannot regulate the output voltage. So you can always step it down, but you cannot regulate it. But LLC provides you the capability of the regulating output voltage. However, the efficiency would decrease if you go to low power or medium power. So if we always operate this in low power, build a smaller of this, and then build a bigger of this, and then we bring it on board of the circuit whenever we need it. So that's what we call it parallel resonant stage onboard chargers. This is a prototype that we built in the lab. That's in my office right now. And then we did some measurements and compared it with the state of the art. The state of the art in LLC converters is this paper published with a research group at Delta Q and University of British Columbia. So we did this, and this is our proposed. So our proposed is this graph, and theirs is this one. So we measured the efficiency, and we noticed that we will have, at the light load, we have 10% improvement. If you go to low power, improvement becomes 10%, and even more and more. In full load, a little bit, maybe like only 1.3%. But if you improve, the interesting thing is, if you improve the efficiency like this, our calculations shown that you can save 1 month electricity bill for consumer, which is not insignificant, right? So that is one work we did. And then we looked at, as I mentioned, integrated onboard chargers. Next step, integrated onboard chargers. This shows the powertrain of a parallel plug-in hybrid electric vehicle. So what do we have? This is, let's say, engine in parallel to your electric propulsion mode. So we have an onboard charger, right? And then we have, this is the large battery, and then we have a step-down DC-DC converter, then we have a low-voltage battery. This is 12 volt, that's 400 volt. Now, if we can integrate this onboard charger with this step-down DC-DC converter, if we can integrate these two and build a converter which does the functionality of two, you're reducing volume by 50%, weight by 50%, cost by 50%, and if we can also use the other idea which I mentioned, maximum efficiency point tracking on this, you're also improving the efficiency, also reducing the electricity bill by 1 month, and it's also bidirectional. You can give power back to the grid, and also you can charge the battery. So many advantages, and another advantage is this. Normally these converters on board of a car, they communicate through CAN bus system. So if we now integrate them together, then you don't need to communicate through CAN bus system. You can locally control them without communication through CAN bus. And so there are many advantages. We have a right now pending US patent and also international patent, which we have filed through the Office of Technology Commercialization. We are waiting on it. So we built this proof of concept initially, as you can see. That's the control board in the lab. This is the Bridgeless power factor totem pole PFC stage, which is bidirectional, and then this is the Resonant DC-DC stage we built in the lab. And then here you can see the components. In this design, we use the silicon carbide MOSFETs. In power electronics, as you know, these wide bandgap devices, they are becoming more and more popular because they have much lower turn-on resistance, so you can improve your efficiency, and also they have really small switching losses. So you can improve efficiency, and also you can increase the switching frequency without worrying about higher and higher turn-on, turn-off losses. So we built this prototype, and we did some measurements that I have some results here. This is the Bridgeless PFC stage. You can see the efficiency improvement from, like, we have measured some of them at 110 volt AC. The measurements we have only done up to, let's say, 2 kilowatts, and 220 we have gone up to 3.3. You can see efficiency improvement. This is our efficiency. This is state of the art. This is our efficiency. About 2% efficiency improvement in the PFC stage, which is still good. But main improvement is in the CLLC stage, which you can see it's a light load. Our efficiency is about 10% improved, which is really significant. And then we looked at some of the chargers, and then we looked at, okay, these are unidirectional chargers which you can go and buy from companies. We looked at it into those. I mean, we are not the only research group that they are working on this. There are a few other research groups in the a lot other research groups that are working in this area. Like University of British Columbia, there's a good research group working on it. Wisconsin-Madison has a good research group. University of Virginia Tech has a good research group. So a lot of universities, they have research groups that they are working in addressing these issues. But I haven't compared these numbers with the research groups. I have compared them with commercially available products because nobody has built this integrated charger and DC-DC converters. They are mostly focused only on the charger itself. So our charger, we want it to be equal to two converters in one package, equal to one charger, and the weight also the same equal, but we have two converters. That means we are reducing the volume on everything by 50%. So this is the way that we have right now. Three of them, they are in fact working on redesigning this for them, put it in a package like this. So this is integrated. We are almost done with building this converter and testing the converter. Hopefully we'll have, in 1 month, we will have everything ready to be able to charge a real car battery. I'll move on to talk about integrated high power chargers. As I mentioned, there are two ways that you can charge your electric vehicle. Either use low power battery or low power onboard chargers or high power offboard chargers. So this is like a low power onboard charger, which can go right now they are looking at the 10 kilowatt power levels. So right now most cars, they have 3.3 and 6.6, and they're looking into moving up to 10 or 11 kilowatts. But if you want to go beyond 10 or 11 kilowatts, then this power is going to be even large. This is going to be very large, and you cannot put it on board. Then you should have an offboard charge. These offboard chargers are really large, and they're expensive. They could be anything from $15,000 up to $60,000. So if you want these electric car industry become more and more popular, how we can do it? Either we need to have a lot of investments a lot of infrastructure in the national charging infrastructure and build so many of them. Right now, Tesla is building its own super fast charge station, but I don't think any other car company is building their own. So they have to follow CHAdeMO protocol and build all these. CHAdeMO is a standard, Japanese standard, which is being popular in the US as well, and all over everywhere. Or we have, charge station owners, like gas station owners right now. They will build their own, charge stations, so many of them, and then they will use to charge. You will charge you to charge your car there, right? So that's another way of, having this, but it's going to take forever. It's going to take forever. So one way is, if we, as I mentioned, like a Tesla Model S has a 185 kilowatt-hour powertrain motor there, and the same inverter, same DC, they are rated for the same power. If I can use this path with only having access to these 3 terminals of the motor to charge this battery, that would be very attractive, because then you can use this proportional machine windings as the power factor correction inductors and reconfigure this inverter and DC-DC converter to charge the battery. It is possible, but it's complicated because you don't want to run the car while charging it, right? If you don't configure this properly, you might run the motor. So we are not the only research group that we have looked into it. There are many research groups that have looked into it, but most of the groups, they have been European groups. I think there's a group in Switzerland, right? They looked into this. There are some groups, but like the method, and also the Department of Energy, to the best of my knowledge, has funded Oak Ridge National Lab to look into this. About like $3 million Oak Ridge National Lab got to do this. So the methods that other research groups have provided, in my opinion, some of them are very attractive, but they have some kind of limitations. One limitation is the fact that most of these methods are single phase. So if you're single phase, you're limited in terms of the power. So what is the advantage? I mean, you can make this one a little bit bigger. It's not 3-phase. Second of all, other methods, they put like relays or contactors in here to separate the propulsion machine from your inverter while charging. That's, in my opinion, useless because, first of all, you're adding additional weight of the relay. Second of all, you're not using these windings, these inductors there, and you're adding them, increasing weight. Other methods, they need to have access to the midpoints of these windings. Having the because they want to make sure that flux, when it enters these windings, they cancel each other so that you don't rotate the motor. We have presented another method that you don't need to have access to midpoints or like neutral point, anything. All you need, you can also, in fact, eliminate this, put an interface here, and only have access to those 3 terminals, and reconfigure the winding and current flow path, and these 2, the way that you can charge a battery. So that is the research that is currently under development in our research group. This is the prototype that we had for a single phase validation, and we have also right now patent. I mean, I haven't updated this slide. We have also a non-provisional patent right now pending on that. So that's all I want to talk about chargers. So a lot of opportunities right now for chargers, how you can reduce the weight, volume, make them more efficient. Now, these concepts are also applicable to everything else, not only for electric vehicles. Everywhere that you need a power supply, you can apply these concepts. Now, other research area that we have been focused on, hybrid energy storage systems. I'm not going to focus a lot on here. I'm just going to pass through it very quickly. So if you look at the battery of a Tesla, you see they are normally Panasonic cells, and its battery consumes 29% or 30% of the weight of the electric vehicle. So normally, we did at some point some kind of studies, and we look at the power to energy ratio of these batteries that they have used in electric car. Okay, if you look at the power to energy ratio, they would see they are vary from 4 to 8. What does it mean? That means batteries, they are tailored toward their power, not toward their energy, right? But battery is not a, I'm not a battery expert, but what I know based on my discussion from my colleagues in, chemical engineering department and material science department, batteries are energy devices. So if you design a battery to have high energy density, you can make the cathode thinner and the battery much lighter. But if you design a battery to increase the power, you need to make the cathode and anode thicker, so the battery will be heavier for the same capacity. So in car industry, they build their battery, they tailor their batteries towards the power and not towards energy, so they become very heavy because they want to make sure that the battery will not degrade during acceleration and deceleration. So that's what they make the battery, oversize the battery. So what I did, in fact, one of my PhD students did this comparison. She looked into comparing two battery cells, almost equal battery cells from SAFT, and we looked at, okay, building the same battery, we want to build this, suppose, a 50 kilowatt hour battery pack using two cells. One of them, this is a high energy battery pack, it's larger and heavier, this is high power, but we need more of these cells to get to the 50 kilowatts. And we noticed that if you use these and this, if you use this one, you need 6 times more number of cells, and that would be, the weight would be 2.5 times higher, and the volume was going to be 2 times higher than if you use this one. So what we can do, maybe we can put supercapacitors, which they have really high energy density, and the batteries, and they build the battery towards its energy, not towards its power, and then we put another DC-DC converter in between to control the power flow between these two, and that supercapacitor will be used as a buffer, in fact. So we worked with a company called Genovation Cars. They had the powertrain similar to this. So they had 2 propulsion machines, 2 inverters, and 1 supercapacitor, 1 battery, and then a DC-DC converter in between. We looked at different opportunities. What are the ways of to control this? So in fact, we did a lot of collaboration with Professor Titz. When one of my students was here before she leaves, and we looked into how we can optimize the control for these two in this structure. And we showed that, in fact, in some of we also built a very small proof of concept prototype, and we showed that we can improve the battery life by 50%, which is not insignificant. So that's one subject. If you remember when I was talking about the onboard chargers, I talked about the concept of reduced state onboard chargers, right? That's where I want to talk about here. If you have a hybrid energy storage system and you have this charger, you can eliminate the second state of your onboard charger. You can incorporate galvanic oscillation in your first stage, and then you can use this supercap as a buffer, so you provide power in every cycle and regulate the battery voltage. Then you eliminate the second one. Now, yes, we can design a hybrid energy storage system. We can put a supercapacitor, battery, DC-DC converter. You can make sure the weight of the entire system is equal to weight of a high power system, single. So you might tell me, why do we even do that? You're increasing the complexity of the system. Yes, the weight is the same. I'll tell this. One is for improving the life of the battery by 50%. So if car companies right now, they're giving 8 years of warranty on the battery, they could give 12 years of warranty on the battery. So that's enough for life of the car. But still, I know it's very difficult to convince many people to build hybrid energy storage systems because it's complicated and it's going to be costly, more costly than only a single high power battery. The only way, which in my opinion, it is inevitable, is the wireless charging. Wireless charging of electric vehicles is becoming more and more popular, right? So wireless charging, there's 2 kinds of wireless charging. One is static wireless charging, one is dynamic wireless charging. Static is like similar to plug-in charging. You go charge your car, you go park your car in your at your home, and it's wirelessly charged, which is attractive because, you know, I mean, we don't want to get out of home and then plug something maybe, right? It's easy. I mean, it's a little bit convenient, but it's not that good, right? It's not that necessary, that urgent. But dynamic charging is very attractive. Dynamic charging is you charge your battery while you're driving your car. Okay? So, for example, in future, we're going to have toll roads, similar to toll roads, dynamic charging toll roads, kind of those. So you can pay, get into that tollway, and then while you're driving, you charge your electric vehicle. So when you're out of the highway, your battery is fully charged. You don't need to worry about that. That's called dynamic wireless charging. So dynamic wireless charging is feasible, is attractive, but again, the power density limitation of battery also is a problem in why, because the car is driving with the 60 mile per hour, let's say, speed of 60 mile per hour. It's very difficult to absorb the power, you know, from the coil underground in a quick period of the time, maybe in a few milliseconds, right? So then you need to have hybrid energy storage system. So we need to have supercapacitor in the wireless charging, so you can dump the power in the supercap quickly and then transfer it to the battery slowly. If that happens, if this technology leads to battery supercapacitor technology, then we can make sure that this is going to be also more feasible. Then car manufacturers will be open to having supercapacitor in their structures. So there's so many things that we can do. There's a lot of things could be done. So the company we are collaborating with is called Genovation Cars. They built the world's first electric Corvette, which broke the world top speed record, 209 miles per hour in the Kennedy Space Center in Florida. In fact, we have a patent that which is based on their sponsorship out of that company. Okay, enough about electric cars. I'm going to make sure to finish the rest of my presentation in 10 minutes. I know it's getting 5 p.m. So the other research area which I mentioned we have been focused is on the more electric aircraft. We've been working with Boeing for the past 3 years on designing regulated transformer rectifiers for more electric aircraft. So traditionally, what is the TRU, RTRU? And regulated transformer rectifier is a unit which converts the 235 volt or 190 to 290 volt AC, three-phase AC output of a generator on a plane to, let's say, somewhere DC voltage 28 to 30 volts. That's auxiliary power supply. So in a car, you have a 12 volt system, right? 12 volt battery, which powers your wipers, your air conditioner, all your infotainment loads. On the plane, instead of 12 volt, you have 28 volt battery, which covers all your entertainment loads. When you're sitting on the plane, you know, air conditioner, all the music player, everything that you see, they run out of 28 volt. So you need to have an auxiliary power supply to provide that power. Traditionally, this is the way that they have used. It's called transformer rectifier units. So they have a big transformer to step down that voltage and then use a diode bridge to rectify it, and then sometimes another DC-DC converter here, to buck converter here, to step it down to 30 volts. That's what like tradition has been done. But so many problems with this. You have this transformer is 350 to 800 hertz transformer, so it tends to be very large. And then there is a harmonic problem. So using this structure, it's very difficult to satisfy DO160, which is the avionic EMI requirements. It's very difficult. You need to have huge EMI filters. So this structure is going to be very heavy and bulky. So, and the efficiency obviously is low because you have those huge diodes. So aerospace industry has looked into designing regulated transformer rectifier units. So that means moving that transformer from the low frequency to high frequency in the middle of this DC-DC stage using an AC-DC three-phase followed by DC-DC single phase. So, and making sure that, so if you design this, it will be easier to design the EMI, which complies with the DO160F EMI standards. And then it could be also air-cooled if you use these emerging wide bandgap devices. So designing this with the emerging wide bandgap device has its own challenges, but the good thing is you can improve the switching frequency and reduce your passive component. As I mentioned, passive components are the largest components. So I don't want to go into the depth of this. I just want to present the results. From now on, I'm just going to show the results of our research to go fast. So this is the PFC stage that we've designed. You can see the PFC stage has 98.5% efficiency, EMI stage 99.8% efficiency, and it's air-cooled. This is the weight distribution and loss distribution. And then we have a DC-DC stage that has 97.1% efficiency, and then the total converter efficiency is 95.4, CHD is 4%, and it complies with the EMI standard. This is the EMI limit, and this is the EMI spectrum that we measured. It's below the 160F, which perfectly is. And then a unique thing about this EMI filter design is that the way that we have designed it, it's only 1.1 pound. It's really light in comparison to whatever you can find at other research group. I think KTH Zurich, they have designed a similar power level EMI stage, which is about 80% larger. I'm sorry, it's about more than 80%. It's like 5 pounds, 4.8 pounds. So this is 1.1 pound. It's like significantly smaller. So we have a new design methodology for it. I know some people, they have class at 4:45. If you have a class, you're more than welcome to, step out. That's okay. So another subject that we've been focused on is miniaturization of power electronics for a variety of applications. So if you look at our motion, our daily activities, there's so many things we have with us that they consume power and energy. You have your PDA, you have your cell phone, you have your music player, you have your, so many components, right? You can look at e-watch. So one way is, if you can harvest energy from these activities, it's really good. You can eliminate many of the batteries, or at least reduce the weight of the battery. You make the battery 1/3 of the size of the battery that you have right now. But then you use the activity or an energy harvesting device to harvest the power and charge this small battery that you have. Okay? Most of the focus that I have seen in the community on this area has been on the energy harvesting, design of energy harvesting device, not on power electronics. So there are many, really a few research groups that they are focused on power electronics. But the problem is, if you design these components for harvesting the energy, you normally design them to operate in natural operating frequency. And if you run, normally the output power should increase by the increment in the frequency. But because they are designed to operate in the natural frequency, if you a little bit deviate from natural frequency, your efficiency will drop. This is not good. But if you put a DC-DC converter in between and design it in a right way, an optimal way, and not only design it, control those in an optimal way, so you go from natural frequency matching to impedance matching, you can always improve the efficiency of these converters. So in that regard, we collaborated with a company, a startup company in Maryland, and then we designed, you can see this green one is the board that we designed. It's 5 by 6 millimeter. The rest are just the gate drive and microcontroller IC that eventually they can go into one chip, so it's not that important. So we designed this as the interface converter. You can see this power level, efficiency of 70% is really, really good. It's not that bad. Like if the size reduces, if you increase the power, if you reduce the power, the efficiency does not proportionally decrease. It drops significantly because then little bit switching loss or little bit trace or conduction loss is going to be significant. So 70% efficiency is really good. The reason we designed this to operate at 2 megahertz because we want it to be very small and we want to be able to publish a paper and say, okay, this is what we did. But then we built a 6-channel version of it for the company because the company didn't care about the size to be so small. They cared it to be small, but not. So this is a 49 kilohertz or 48 kilohertz switching frequency. So it's much larger than what you see, but it can interface 6 different channels and give you a good output power, and then you can step it up and then connect to a load and utilize it. So that company wanted to, use these they call it like wind. The technology was based on wind induction and vibration, as opposed to wind rotation. So we designed it and we published a paper in Transaction Power Electronics. While I was working in that area, I started talking to one of my colleagues in mechanical engineering department, Professor Sarah Bergbreiter. She works on the micro-robotics. And so these are some of the micro-robots that you can see, Berkeley, Harvard. This is the flying robot. And this is the jumping micro-robot that Professor Bergbreiter's group, they have designed. So she mentioned to me that one of the challenges that they have in micro-robotic community is the size of power electronics, because robots themselves could be very small. These are the biologically inspired micro-robots. They're very small. However, their power supply tend to be larger than the robot itself. If you look at this robo, this small like flying micro-robot, you can see there are wires connected to it because power supply is larger than that, and it can fly as long as you have wires connected to it, right? But if you make a power electronics very tiny, you put it on board somewhere in here, then you don't need to. It could be autonomous, completely autonomous. So we initially did some work with Sarah. There are so many challenges in making the power converters very, very small. These are some of the challenges which I have added here. We designed a very simple flyback converter followed by an inverter, and we tested under microscope, and we looked at the shuttle movement under microscope, and we published a paper out of this, and then we extended that work to gap closing electrostatic inch worm motors, and then we designed this other converter, which this is like the back, this is the front of the inverter, and these are again microcontroller. And we looked at the shuttle motion. This is the way that it operates. And also we published another paper on that together. And we measured the efficiency. You can see the efficiency reaches as high as 75%. One of the uniquenesses of this converter is that not only it can step the voltage up, let's say from a 2-volt onboard battery to 200 volts, but also it can convert it to either sinusoidal or trapezoidal or step function or whatever you need to actuate the robot. But also, it's bidirectional. So these actuators, normally they are capacitive. They have capacitive nature, so they do not completely use whatever energy is given to them. So they waste it. So the way that we've designed this, so you can take the power from one wing or one leg, which is unutilized, and give it to the next leg, or give it back to the battery, so you can enhance efficiency even more. So we designed just a power supply. We tested individually. Right now, Professor Bergbart is in sabbatical, so we've been looking to collaborating and writing a proposal to get funding to take this to the next level, put on a real robot, and test it. So this is a research that we have done till here, but we haven't really put it on board of robot. It has a lot of challenges to put on board. Last subject. So everybody knows of social media nowadays. Everybody knows Facebook, Google, and they have data centers, right? We have, it's based on my knowledge, by 2020, 10% of the electricity will be gone through data centers networks. That's significant. 10% of the electricity generation is going to go through data centers. Everywhere there, they need data centers, and biggest data centers are in this country, right? So this is general structure for a data center. The way that they have a power grid, they have a 60 hertz transformer, they have an AC-DC converter, which converts 110 volt or 102 to 120 volt AC to 400 volt DC. And then you have another large DC-DC converter, which makes it 12 volt. By the way, there are like 2-3 different methods. This is one of the common ones. And then there is a huge DC bus. And then these are connected to all these motherboards that they save the data, right? So this is traditional way of doing it. In this way, there is a 12 volt bus here. And depending on what is the power, total power, you will have a huge current. You will have really high current through this, and you will have large conduction loss. Okay? Now, people are looking into changing this structure. Instead of having this DC-DC converter here, put DC-DC converter on the motherboard. Instead of having a very large DC-DC converter here, you put small DC-DC converters here on each motherboard. Each motherboard, let's say, is going to be in the order of 1 kilowatt. 750 watts. So this is the structure that people look at. Because if you do this voltage is 400 volts here, so there's going to be a huge current. There's going to be very low current passing through, and efficiency will be better. So this is a new structure people look at. So the way that we got involved in this, there is a society of IEEE, is Institute for Electrical Electronic Engineers. There is a Future Energy Challenge competition, International IEEE Future Energy Challenge competition. Teams from all over the world, they can design converters and go compete on a subject. So this is one of the very important subjects today in the data center. So the subject of the competition this year was to design in these DC-DC converters for 750 watts. So we built a team of the students in my research group, and with 3-4 undergraduate students and 2 graduate students to participate in this competition. We use this topology. This is also half-bridge LLC resonant topology. I don't want to go into how does it work. So we use that topology, and we designed this converter. We participated in the Future Energy Challenge, and we got the best presentation award. I guess we were the only U.S. team who got an award. So that was a good thing, and it was the first time that University of Maryland was participated in this competition. So the input was 400 out of 12. And these are like some of the numbers that we measured. Unfortunately, our converter has a limitation in terms of the temperature. It's not really robust in terms of temperature. So right now, we are redesigning this converter in the lab to improve the efficiency and thermal performance of the converter. So in general, the research and development in our lab at the University of Maryland Power Electronics Laboratory is focused on modeling, simulation, design, and development of innovative, compact, highly efficient converters from milliwatt to 10 kilowatt. I'd like to thank our sponsors. These are the sponsors that we have had in the past 6 years. And we have some other projects in the lab that I cannot talk about them because our sponsors don't want us to talk about. One project which I didn't talk and I can talk about is a pyroelectric energy harvesting, which is another subject that we are doing. But this is not all we are doing. We are doing even more than this in our lab. So I've presented some of it just for you to get familiar with what we have done. And also I want to mention again, some of you, I know that we are in the process of starting a TERPS electric vehicle racing competition. To build a small car and then go to like TERPS racing team. So if you're interested, send me an email. Hopefully in a couple of months we'll be able to initiate it and then maybe even offer a capstone design course. So with this, I'm open to questions.
Wonderful.
Thank you.
Time for a few questions.
It could be anything. It doesn't need to be technical.
So Alireza, how do you go by designing the systems initially?
So
what are some of the approaches?
So we initially look into, depends on the case, right? Depends on the case. So in some cases we know.
They have too many components they're coming together. They have to do this complex work.
Exactly. So we need to know like what is the power. Power level is the important thing for us. And input output. We know some basic inputs that it's our power levels. And based on that, we need to have a systematic approach, exactly, a systematic way to design the components. But initially we choose the values that they satisfy our requirements in terms of efficiency, in terms of power density, in terms of, then we consider many different things like a switching frequency, like the way that we design the PCB layout and all those things to make sure no interference. So we have a systematic way, but it's not like straightforward. We always go in iterations and choose the components. Yeah.
So I imagine drone manufacturers must vary in the technology of the base power electronics.
So exactly. So we haven't worked on it, but a couple of the UAV manufacturers, they have to come and talk to me. So they're very much interested in 400 to 12 volts that we are designing, because normally these drones, they also have a 412 volt battery. Some of them also are tethered drones, the ones that they accompany a person. So they have drones and they have a wire that transfers the voltage from the ground to, let's say, to 400 volt, and then there you need to step it down again because you want to reduce the losses. They step it up in the ground and then they transfer it to the sky and then step it down again. So they're interested in that. I have talked to a couple of companies, but we haven't started working on that. But same principle of 412 volt design is applicable for that application. But it's completely valid. Thank you.
So, next time, just a quick question. So, like data science and machine learning, is emerging in many fields,
right?
Engineering and sciences. So, I was wondering if, there are venues in power electronics where, data, like the high dimensionality of data is a bottleneck and needs to be addressed at the same time as, the electronics.
It could be. Honestly, I mean, like if you're optimizing something, like we have looked at some data perspectives, let's say, okay, or like I don't know, like the machine learning. Machine learning is definitely useful in power electronics because everything, power electronics is in fact, designing converters which are part of a system, right? And when you have a system, machine learning is important to train or use methods. I haven't focused on it, but I'm open to those kind of collaborations and look into how we can integrate machine learning or different, control and optimization techniques into our systems.
So how about the data obtained by observing one or many drivers? Exactly, having spikes for one driver, maybe a group of drivers.
I mean, yeah, that's
how they use it.
That could be used for many different things. In fact, because we work on power electronics, we don't do like data, gathering. But there are a lot of people that they were, for example, I think that there's a professor at the University of Michigan, Jesse. I don't remember his Grizzle, yeah, they do a lot of this work, so they do a lot of data gathering, and this is in fact, I'm hoping, my own hope is, like after we do this electric vehicle like race team, and my idea is to make it even a smart autonomous vehicle, so there's many different interesting concepts that we can integrate into that, and also we can use this to gather data as well on campus of the University of Maryland. That's something could be used for our research, but that's true.
So you talked about dynamic charging. I was thinking about all this multifaceted energy harvesting, like wind, like traction, like solar. Why can't we use some of those for this dynamic?
We can, definitely.
Is it because of the cost?
I mean, but it could be used. Those are definitely, so if you are in the middle of a road. It
could be multimodal.
Of course. Yeah, most probably the power of those will come through these renewables, or we call it distributed generated units. So the power will come, and it will be forwarded towards the wire path that will be distributed. Yeah, this transmission path which are distributed on the road. Exactly. Yeah.
Any other questions?
From students.
Before we thank our speaker, I just want to indicate again that this seminar was sponsored by 2 of our industry partners. And if some of you are interested in doing internship with one of them, please see Jeff Coriol in our External Relations Office. This is a great time to plan for the next summer. I know this is something that's probably exciting to some of you. And also Professor Khaligh is, if you want to talk to him regarding graduate school, you know, working with him, this is the time to do it. So let's thank him again.
Thank you.